Today I want us to talk about composite functions, the application. Of course, they have a lot of application. I'm just going to mention a few things. But in this course, why do we use composition and where do we use them? We use them to actually simplify range problems so that they become easy for us to find the range of a complicated function. And also we use composite functions to actually find other functions or create other complicated functions from our basic functions that we've studied so far. So those are the two, but those that are happening outside in real life or in just the real application, that is like where can we see them, maybe in business or somewhere. Maybe we'll touch a little bit, but for now I just want us to have the basics of what this is supposed to be a P composite functions. Composite functions, or the composition of two functions. So the first thing that I want us to suppose f of x and g of x are functions, and have respective domains d of f and d of g. All right, so we have these two functions. What do we mean by the composite or the composition of f and of f of x and g of x? We write first f, let me do this. This little circle here, this is just a little circle, and then we put g of x, g, and then we put that g of x. And then we say that this is how we write it, and this is what it actually means. It means that I'm gonna take this x, plug it in g of x, get g of x, and then plug it in f of x. So this is the same as f of g of x. That's what this thing is actually, the actual meaning of this thing here. This is just a small circle that is saying we want the composition of f and g. So how does these things actually work, and how do we actually perform some operations here, or this composite operation? Basically, this is saying you have x here, and of course this x here, that you take it in the domain of g of x, and then you take this x, and then you plug it to g in this function, and then you get the output g of x. And then after that, that output will be one number amongst the numbers that are in the range of g of x. And then once you have that output is then plugged in f, and then the output that you're gonna get, remember that we're taking this output, and then you take it as an input, you plug it in f, and then you end up having f of g of x. That's what this thing is actually saying to us. What does this mean for the domain of this composite function? So the domain of this composite function works like this. The domain g of x is the set of all input values that are making g of x defined. So that's the domain of g of x. But now, what is the domain of f of g of x? Remember that now we are selecting elements that are outputs of g of x. So it is a set of all possible x values that are in the range of g of x, that is making f of x defined. So in a nutshell, we can just say that, okay, the domain of F, the composition of F and G, or I can just write this, is the set of all values. I'm just gonna put like input values because X is an input. Set of all input values X that makes both G of X and F of G of X defined. That's the set of all. That's what is all about the domain. This is just theoretically. When you are actually finding the domain, if I give you a function, just use the normal way of finding the domain. And if you're not getting how to find the domain, you can think of like this, that okay, fine, there is a video for it, you can check it out, or you can have a consultation if you still have some questions on the domain. But now let's look into this process here. I have X, and X goes through this thing here, or this rule G of X, and then G of X processes the out and then gives some output, and then this output here is then taken again, plugged inside F of X, and F of X processes it out, and then you end up getting the final output there. And look into this here, we can think of this as a process. This is just a process. You have some ingredients here. You have some ingredients, right? And then these ingredients, right, they are placed inside some machine, and then at this point here you get some output, and this output I'm gonna call it output 1, and then this output again is placed inside now a different machine to refine it, so that you end up getting a final output here. So this output for this one here, it becomes an input of this final machine. So how one would think of this process? This process will be something like this. I have let me not say a chicken here. I have a rooster. The rooster is here. A rooster is something of this kind here. I'm trying here to have something that is like this, and then I have this rooster here. I'm trying here, and of course it has something there. It has an eye, and it has some sort of a wing there, something like that. So you have this rooster here. This rooster, let's say we cut its neck here, and then we take this rooster and then we plug it into a plunger machine. We have a plunger machine here, so that it takes the feather out, right? So it's gonna take the feather out, right? So we have a rooster, which is an input, and then we plug it inside this machine here, which is G, and then this G here is a plunger that is taking out the feather. And then now, once the feather has been taken out, we have our another process here, or another machine here, that is our F. This machine here, it cuts the rooster into pieces, and then we actually end up now having our final output, which is meat pieces. This is one way to look into composite functions. Another way to look into that, you can think of this. I have this bunch of products here, right? And then this bunch of products, you sell them. After selling these products, right, and then you get, this is our G. G is saying sell these things, and then G will calculate what is the revenue that you will get after selling these products. And then F here, what will F actually do is going to say that after I have sold these things, I am going to take the revenue and then subtract the costs. So this F here can actually make sure that it takes that revenue and then it calculates so that it brings you profit. That's how these composite functions actually work. But now in maths, how do we actually deal with this? Because of course, when it comes to the range of this particular function, we'll deal with it at a later stage, because that's actually the main goal for us to actually use these composite functions. How does these functions actually work? I want us to take a couple of examples and see what is the composite, the composition of f and g, or the composite function that is actually taking this input x here. Suppose I'm gonna say this. Suppose I have f of x, and f of x is equal to 2 to the power x, and I have g of x, and g of x is equal to x squared minus a 1. And I am saying to you, I want you to find the composition of f and g. This is your A. B, I want you to find the composition of G and F, and I want you to find the composition of F and F, and then D, I want you to find the composition of G and G. G and G. Remember, this is just a small circle there. So we have this, which is just the symbol for composite function. So we have these nice things here. Before I can proceed forward, I don't want you to get lost. Sometimes you find someone writing that the composition of f and g is this. Someone you find writing the composition of f and g is written this way, right? And someone else, you might end up finding that they have a certain notation like f of g of x, or someone might decide that I'm just gonna use this f of g of x. Oh no, this one is already there. I want to tell you that this and that they mean one and the same thing. It's just for notation purposes and a preference for a certain human being deciding that I like things this way. Now that we have that, we said that when you want to find this, I wanted to take some x, plug it inside g. So we're trying to find our solutions here. Of course, we're gonna start with A. Our A is saying I want to take x and I want to plug it in g first. So I want to plug it in g so that I get g of x. What is g of x? G of x is given there, right? So it is given there. So g of x is the same as x squared minus 1. Now that I have my g of x as x squared, I want to take that output and then I want to plug it in f so that I get f of, we had f of x, right? But now I am not taking x, I am taking this input here. So I am going to have x squared minus 1 instead. So this will end up becoming, at the value of x, I am plugging that, which is this equation there. So I'm going to have 2 to the power, at the value of x, I'm plugging x squared minus a 1. That's what is happening. This simply means that f composite g of x is just the same as 2 to the power x squared minus 1. And then let's go to B. B is very simple also. And then when you look at B, I want you to take X first, and then I wanted to first plug it in F. So this one, I want to plug it in F so that I end up getting F of X. And then what is F of X? F of X is 2 to the power X. And then I want to take this output here, and then I want to plug it in G so that I get some G of something here. We were supposed to get G of X, but what we are plugging here is the output here, not that X there. So here we end up plugging in 2 to the power X there, which is just the same as 2 to the power X. Remember that this is X squared, so we're going to end up having a squared minus a 1. Therefore, the composite of F and G of X is the same as when a power of a power is just the same as 2 to the power 2x minus a 1. If you want to simplify, you can go further and say that this is the same as 4 to the power x minus a 1. But this one is enough, this one is enough, or you can go like that, because 2 to the power x, okay, let me fix this so that you can see. This is 2 to the power 2. You can switch these things around as long as this is defined. And then you have minus 1, and 2 to the power 2 is 4 to the power x minus a 1. Now we are done with number B. Let's look at number C now. So whenever you are dealing with number C, this is very simple. Number C is saying that I want you to take x first, and then you plug it in F. So I have my x. I wanted to first plug it in F, and then remember that in C we want to find the composition of F and F. So I want to take this x, plug it in F, get some output which is F of x, and F of x is the same as 2 to the power x. That is what is F of x. Now that we have that, I wanted to take that output and then plug it inside F to get F of that output, which is 2 to the power x. And if you look into this 2 to the power x is replacing x in F of x, and F of x is 2 to the power x, so you end up having 2 to the exponent 2 to the exponent x. So x is replaced by that nice thing there. And take note that this 2 here is the base. It's not the multiplication of these two, so we cannot just decide I'm just gonna change that. And then number D, we are looking for G composition, the composition of G and G. And of course, I'm taking X and I plug it there, so we'll get X, and then I move this X, and then I plug it inside G, and I get G of X, which was equal to X squared minus 1, and then I take this output, and then that output there, I plug it inside G, and then I get G of that output there. So what is G of that output? Whenever there is X, I'm plugging that output there, I square it up, I separate a 1. So that is therefore the composition of G and G of X. This is the same as that thing there, which is X squared minus 1 squared minus 1. So you can simplify this, or you can leave it like this, because this is not a simplification problem. It is what I call the composition problem. We can also take another example here and say this is going to be the next example. I'm just gonna do this example and the next one, but the next one will be just illustrating how you can utilize this to find the domain of a very complicated function. The easiest way is just look at the function and deal with it as it is. So suppose now I am saying that I have saying that given given our f of x is equal to root 2 minus x, and g of x is given as let me say we have square root of x. Let me just say plus a 1. I'm just gonna go with root and root, and the question is find f composite g of x, but we usually don't use that. We just say find this. So we're gonna have an a, and then b is going to say g composite f, and then we're just gonna find okay, let me also add c, which is g and g, and then d, which is f and f. How do you find this solution? Of course, you can continue like that. What this is saying is this: you take, this is going to be a, you take x and plug it there. So you're gonna have your x, and then you plug it in g, you end up getting g of x. What is g of x? G of x is the square root of x plus 1, and then you take this output as it is, and then you plug it in f, and then you get f of, this is what you are plugging, so it's gonna be the square root of x plus 1, and then after that you're gonna get the square root of, this is f of x. F of x is that, and it has a 2. Where there is x, I'm gonna plug in that thing, so I will end up getting the square root of x plus a 1. That's what you do. And then therefore you can just say, okay, the composition of f and g of x is the same as 2 minus square root x plus a 1. The same thing for b. You do the same thing for b. You take your x and then you plug it in f first. So we're gonna plug it in f. We end up getting f of x, and f of x is the same as that, which is 2 minus x, and then I take this whole thing, which is an output that I got, and then I plug it inside g, and then g is actually going to be g of this thing that we're getting here. So I'm gonna plug in 2 minus x in the value of x. So you go to g is the same as the square root, x is this whole thing here, so we're gonna have a square root of 2 minus x, and then you have that plus 1 there, which was this. So the main thing, actually, whenever you have this, you just take g of x, which is that, and then you place it in the value of x. And when you're looking for this, you just take f of x as it is, and then you plug it in the value of x. Now when it comes to this part here, this is going to be simply because I'm gonna take this thing as it is, and then this is going to be equal to as it is, the square root, but in the value of x I'm going to plug in g of x. So I'm gonna have the square root of x plus 1, but in the value of 1 I'm still gonna have that. And then when it comes to this one here, I'm gonna take this as it is and then plug it in the value of x in f of x. So this is going to be the square root of 2 minus, but in the value of x I'm plugging f of x, which is 2 minus x. So this is how you end up going with this. Now I want us to actually find a nice example. This is example. How can we actually use composition functions to actually find, or how can we find the domain of the composition functions? Is that even hard? So this example would be saying find the domain of I want to find the domain of f of x is equal to, let's use log. I think we have actually neglected log functions, and this one I'm just gonna put here the base. I just want to use a 5, and then I have an x there. Can we find the domain of this? No, this is way too basic for us. I want us to have let's say x squared minus a1. That's it. How do we find the domain of this nice thing here? So we're just gonna analyze it a little bit. Of course, if we were using the standard way of finding a domain, then this question was going to be easy. But I want us to analyze it in terms of composition functions. Now, if you look into this function, we can see that what is basically happening here, I have some function g of x that is inside the log function here. So I have this function, and it is x squared minus a 1. And also here I also have, if I were to replace this thing by just x, I would end up having some f of let me just say f of x. This is going to make things harder. I'm going to have some h of x is equal to log 5 x. So I will have this. I know how to plot this, I know how to plot that, but the issue is with that, I don't really know how to plot that thing, because I have this x squared sitting inside there, and I have this one there. Now, how do I find now the domain of actually this particular function here? So this is not a matter of hard. It's not that hard, but it's just that you have to place your mind into it, and then you will be able to solve it. And also, just like any other problem, you will notice that in most cases when it comes to this maths, especially when you're still in your undergrad, that it's highly impossible to really know what are the application of this thing. Is this the right thing for me? Is this not the right thing for me? That's not really an easy way to look into this, because most of these things, they start to make a lot of sense when you are starting to do your honors level. When you start to see now, okay, there is some differences now. You start to see, if I'm doing applied maths, now this is what is happening. If I'm doing pure maths, this is what is happening. If I'm just doing this course, this is what is happening. And if I'm doing a different course, this is what is happening. For instance, in this course, you'll find out that you will be doing a lot compared to someone who just have majored in maths. You'll be doing a lot because there is a lot to be covered in this course, because you only do maths, I think, only, I mean the calculus side of things, you only do it once. You only have 6 months to do it, so we end up covering a lot. So with that being given, things, they start to be different here and there, and either they look hard. Sometimes you see that we are not actually understanding almost everything. Is because we don't have time, because there is a lot to be covered here. But if we were to continue and we had time, you would see actually that this actually makes a lot of sense. I have drawn these Cartesian planes, 2 of them. One of these Cartesian plane is for this curve, and one of this Cartesian plane is for this curve. And now of this function, and of course it's that function. To draw this function, this is an easy function. You know that y is equal to x squared looks a lot like this. It looks like that. And then -1 is saying that shift this curve by 1 unit down. So this point here would be somewhere there. So we'll end up having a curve like this. Remember that we are shifting everything as it is. and we are not shrinking or compressing anything here. So this one was x is equal to x squared, and then this one is x squared minus 1. A minus means we're going down. Okay, now that we have drawn that particular function here, you would ask yourself, what are the x-intercepts? When will this thing be equal to 0? Of course, the first thing to look at, when you're looking for the intercepts or solving this or factorizing that, you look at the factors of this that are making that equation equal to 0. So if I'm plugging a 1 here, if I'm plugging in a 1 here, I will get 1 squared is 1, 1 minus 1 is 0. So 1 is one of the solutions. So this point is 1. And if I'm plugging in here minus 1, which is also another factor of 1, you can see that I'll get minus 1 squared is 1 and 1 minus 1 is 0. So we'll also get another point there. So this one is just like that. But now, how do we end up plotting this nice function here? This becomes a little bit tricky, but one thing that I wanted us to note here is that whenever you have a number is equal to a base, and this base here is equal to is raised to an exponent, this is equivalent to saying you have an exponent, and this exponent is equal to log base, and then this one here is equal to a number. So you have this nice thing, right? So this one and that one, they are actually equivalent. So if we, let's say now we come back here and we look at h of x is equal to log 5x. So instead of f of x, I want us to write, okay, we had h of x, and h of x is log 5, and then you have an x there. So I want us to change this first to just, instead of having h of x, I want us to just write y instead, so that is going to be easy for us to actually do the conversion here. I want us to move a little bit. So whenever I have an exponent down up there, and we have a number, you have a base, this base becomes a base in the log function, and then this number that is inside here is the one that was outside there, and then this exponent is outside. So I want us to analyze here. So this one here is the one that is inside, which is, let me use a different color there, which is a number. So x is the number, 5 is the base, and then y is the exponent. So this function now is the same as, I wanted the number to be here according to that. So the number is going to be x is equal to base, which is 5, to y, right? But if you look into this function here, x is a subject of the formula, and then we have y is an exponent. If we wanted to make y a subject of the formula, we have to interchange x and y. So this one here will actually end up having y is equal to 5 to the x. We know how to plot this, but we don't know how to plot this one here. But interchanging x and y, it means that it is a reflection of that along the y is equal to x. Okay. How does this function look like? When x is equal to 0, y is equal to 1, and it doesn't touch the x-axis. So that function here, it looks nice like this. So this one is y is equal to 5 to the exponent x. And if I'm placing here this line here, this is the line y is equal to x, and then it goes nice like this. If I am saying that this is my mirror, I'm standing this side, what will I see on the mirror? Remember that when x is equal to 0, y is equal to 1 there. So this point here in the mirror, remember that in this mirror, when I am going this way, the reflection is going to be that way. So if I'm standing here, I will see what I'm standing on the mirror as that. So 1 will be at that point there. So this y point, which is y, it becomes the x. Y-intercept becomes an x-intercept. Y-axis become the x-axis, and the x-axis become the y-axis when you are actually considering that mirror. And then if you look at the x-axis here, this is a horizontal asymptote, so this curve is not touching it. So when you're looking into this mirror, it will become this thing here. I want to use a red. It will become this. This is going to be the asymptote now. So what this thing is happening here, it will be happening. This curve is not going to touch that. So we're going to have a nice curve like this. So this one is x is equal to 5 to the exponent y, or the same thing if you rewrite it, it is the function h of x is equal to log base 5x. So this is our h of x. So this is g of x, so we have that. Now we have drawn our curve here. We just drew this curve. We just drew that curve, and then now that we have drawn the curve, I can erase these things here. I can erase these things here. The question here is very simple. Is what is the domain of that function? So if you look into this drawn function here, you can see that the domain of h of x is the same. I can just say h. X is an element of real numbers such that you can see that x is only going to take values that are above 0. It cannot take any value that is negative. It can also not take 0 because this function is not going to touch 0. So as long as we have x is greater than 0, we are fine with the domain of that function. Now that we have the domain, it means that whatever is here, we want it to be above 0. Okay. Now, remember the question was not to find the domain of this. We want to find the domain of that function. And if you look carefully in this function is the same as if I take this function here and I plug it in the value of x, this is the same as h of g of x. So it is the same. So that is why I'm splitting it into two. I have this part which is inside, and then the outside, replacing this by x, I have that. Now, how do I find the domain of that function then? You come here. Remember that the output of this function is the one that becomes the input for that function to get that, which is the same as that. So how do you end up finding the domain? You go back to this function and say, I want the values of x, because I want to plug in some x, such that those values are bigger than 0. So if you look at the range of this function here, the range, looking at the range of g, you will find out the range of g start at this point, which is -1, and go all the way. So it is a set of all y is a set of all real numbers such that y is greater than or equal to 1. So this curve here is saying I can offer you this much as a domain. Do anything that you want with it. This one here is saying I want x greater than 0. So I'm gonna come at this point. This is supposed to be -1. It's a mistake because this is -1 here. So fix this, is minus 1. So this one is saying I can give you this much, and this one I'm looking for that. So in other words, this y here will become an x in this curve here. So basically, what will this mean? It means that, okay, sure. What we are going to do here, I'm just gonna take what I need and leave you with everything else if you have access, but I'm gonna take what I need from what you are offering. So when you look into this, this means that, okay, the domain of this particular function here, which is supposed to be taken from this range here, x is giving you everything. I wanted to take y that is greater than a 0. That's what this curve is saying. I want to take that. Now that I want to take that, I want to go back to this curve here. What are the values of x that are actually giving me y bigger than 0? So I come here. Is this value bigger than 0? Yes. Bigger than 0? Yes. Bigger than 0? Yes. Bigger than 0? Yes. But once I start to be in that point, it's not bigger than 0 anymore. So I don't want the values of x that will end up giving me these negatives up until 0. So all these x values, I don't want them. I only want this portion here which is bigger than 0, and that portion that is bigger than 0. But what are these values of x that are giving us that portion and that portion? You will find out that as long as you have x and x is less than minus 1, and x as long, let me not use and here, or I have x is greater than 1, I am getting a positive value here, which is what is needed there. So the domain of this function here is going to be, the domain of f is going to be x is an element of real numbers such that x is less than minus 1 or x is greater than 1. Another way to rewrite this, let me go down a little bit. I can just say x is an element of real numbers such that x is taking all the values from negative infinity, because negative infinity don't touch it until you have 1 less than, which means you don't touch that, or it's a union, and then you're gonna have a 1 is not touched up to positive infinity. So this is how you find the domain. Quick review is, first, take this function that seems to be sitting inside the basic function that you know and pull it out. And then once you pull it out, pretend that this is a variable x, and then you have a new function h of x, which is that. Then plot that inside function if you can, and then plot this function if you can. And then you look at the domain of that basic function, you find it, okay, this is the domain that I'm looking for. And then you come to this function, you look at the range of that function, you find, okay, this is the range. And then once you get that range, you say, okay, this is the range of that function. So once you have that, it means that this curve is offering that range. Then you look at this one, what is the domain of that? In other words, what are we looking for from what is offered? This is in terms of y, this is in terms of x, but it shouldn't make things hard for you, because that's what you're actually looking for. Because y this side is an output, but it becomes an input that side. So you say, okay, fair. From this in terms of y, this was my domain, x is greater than 0. I am looking for y being greater than 0 in what you are giving. From what you are giving, I can see that this one is more than what I'm looking for. So I want to take that. You go back to the curve and then you check what are the values of x that are actually producing what I'm looking for. And then you take those values will actually become the domain. That's how this thing is. Very simple, very straightforward. But when it comes to domain, this doesn't make sense whatsoever, because you can just solve this. You know that the domain of a log function should always be the value that is inside should always be greater than 0, and then you solve it using inequalities. But this is an illustration. I think I will end there.